So today's paper's title is HandNeRF. It's neural radiance fields for animatable interacting hands. So to give a general overview of what it does, it's about, let's say, for a scenario where we have a video frames of hands interacting, we have images of that scene from multiple angles, and it's about exploiting those multi-angle views to render the hand in different poses. So let's get into the details. So before I get into HandNeRF, a brief overview of NeRF for those who are not familiar with NeRF. So NeRF is about, let's say we have a 3D scene. We have a scene, let's say, and we model the scene using in a 3D coordinate system. And what NeRF does is, let's say we want to look at the scene from a particular viewing position. And so what we do is in every pixel of that viewing position, we assume a ray going through that pixel into the 3D scene. And then we map the coordinates along a particular ray using a multi-layer perceptron to these two values, which is just a single RGB value, and as well as a quantity called the density, volume density. So what volume density is you can think of it as something called objectness, meaning whether there is a solid object present at that x coordinate or not. So this is a value usually between 0 and 1, and higher values would mean that there is less chance that light going through that particular x coordinate will pass through that object. So for like air or empty space, this volume density will be low. And so, yeah, like I said, so we do this for multiple angles, for a single scene, and we cast a ray into the scene, meaning we just simply assume a line, going through a particular pixel of that particular viewing direction, and we just feed this 3D coordinates into an MLP, as well as the angle of the ray in these two parameters. And then, yeah, like I said, it maps to these quantities, RGB and volume density. And the way, like, there is also a lot of thought that goes on into which particular X coordinates to choose. So usually so this is called, like, when we feed an X coordinate into an MLP, we call it basically a querying the space, 3D space. So which points to query, like there are also strategies about which points to query. Usually the points to query would be much more higher frequency in regions where there is actually a chance of there being some objects. So in empty space, you usually pick less number of query points, and in these dense regions, you pick a lot of query points. So in this paper setting, it's NeRF, but it's okay. Before that, there's another portion. Yes. So let's say we have along particular array, we have generated these values. We have the volume densities, as well as we have the RGB color. And then you can use this for integration formula to sort of get a particular color pixel value for this particular pixel that you are in the image that you are seeing. So yeah, like you can see from the camera point, you cast a ray into the scene, and then you get the volume density across the whole ray, and then you input the volume density as well as the coordinate values and the color value that you got, and then you can use this formula to get the expected color that you'll see when viewed through that particular position. And this this output is, you can visualize it sort of like this. It's not exactly a mesh, but it's also a volumetric representation. So a mesh would be something like a polygonal, a bunch of polygons forming a 3D shape. But in here, it's a completely continuous representation. So you can even generate a depth map from this kind of representations. So yeah, in this paper setting, it's mostly based around the setting of MIP-NeRF. So MIP-NeRF basically in the traditional original NeRF, you assume a single ray going through a particular pixel of the image that you want to form. But in case of MIP-NeRF, you don't assume just a single line going through it. You assume sort of like this conical structure, and and then you divide it into multiple sections, which become frustums, and then you model each of these frustums to using this kind of representations where, the mean point around this is this x, and then you also have a variance term sigma, and then you have the rays direction, viewing direction d, and then again it gets mapped to the same quantities, c and color and volume density. And while there are a few more contributions in MIP-NeRF, but for the purposes of this paper, this is really all we need. And yeah, now getting back to HandNeRF. So this is the general overview. We will get into each of the components one by one. But to give a highly generalized overview, you have a scene, which you call observable space, which is, let's say these two hands. You have a video of these two hands, and then you model the frames in a 3D coordinate space that you call observation space. And then you extract some pose for that particular scene that you are seeing. And then you also extract a mesh, 3D mesh, and then you put it into this deformation field, as well as some coordinate points from this observable space to map them onto this canonical space. Again, I'll get into more details about this. Hang on, this thing. For pose-driven hands modeling, we introduce post-condition deformation fields that warps the observing rays passing through both hands to a shared place where a static NeRF is established for one conical hand. So what this means is that, let's say we are trying to model again. Let's say we have some hands. So again, like I said, first you model the scene that you are seeing as the observable space. So which is the X observe. Okay, we'll see that later. But then you use this deformation field to map them onto a canonical space. And so this canonical space, it sort of gets vague as to what exactly this canonical space does. But from what I understand so far, it's basically a standardized space of sort for both the hands or all the hands you see, where you map this an individual hand from the observable space to a canonical space. And for both your hands, even though there might be two hands in the scene, you still use one single canonical space. So this canonical space, you can think is more like a standardized representation where its only goal is to learn about the hands, learn about the NeRF representation of a particular hand. So in traditional NeRF, we had a single MLP outputting both volume density and color, but in this case we use two different MLPs. So where for the first one that gets the volume densities, this IPE is called integrated positional encoding, proposed by, this is proposed by the I missed it. It's the MIP-NeRF paper. For now, you can just think of it as just some sort of transformation that you apply to these two values. And then you have something called also feature field. It's called distillation field, but I'll get into the detail of it later. And then, yeah, you also have another MLP where you take in the transform version of this viewing direction, then this distillation field for volume, and this latent code to model the subtle texture differences between frame. Again, I'll get into each of these quantities in much more detail. So yeah, to start off with the deformation field that maps from observable space to canonical space. So given an arbitrary hand pose, the deformation field is intended to learn a mapping from observation space to a canonical space. Yeah. HandNeRF follows the settings of Mano with the 16 hand joints, the pose parameters P, the canonical mean pose P bar, and blend skinning weight, this WB, which is a 16. So basically, so this from Mano is again a different paper from 2017. I myself am not clear about everything about this menu, but I might be wrong. But from what I get so far is that so we use this Mano technique to get a mesh representation of this observable scene that we are seeing, and then we use this mesh representation and also the pose as an input to this deformation field. And the pose would be I guess, these representation of a hand and like 16 joints in one particular hand. And the blend skinning weight is, I'll get into that later. It's about, it comes into play when you try to model the animation of the hand, motion of the hand. So yeah, similar to many classic mesh-based methods, Mano uses linear blend skinning to accomplish skeleton-driven deformation for mesh vertices. It models the coordinate transformation between poses as the accumulation of joints, rigid transformation weighted by the blend weight WB. So I'll come back to this, but let's review what linear blend skinning is. So let's say we have, let's say we have a mesh representation and we have certain joints. So in hand's case, those would be the 16 joints, which have 3 coordinates each, of course, 3 coordinate values. And so what linear blend skinning is about is for every single one of these joints, they sort of have a weight value associated to it, which comes into play, let's say, when these vertices are moved. Let's say, yeah, this red one is sort of moved down so that it forms a twisting formation. The weight value, the linear blend skinning weight of that particular joint or vertex will determine to what extent mesh points within the region will be moved. So yeah, for for an illustration of this, you can look to the right. Let's say point 1 and 2, and then you sort of twist them. Then let's assume that both the vertices 1 and 2 have the same linear blend skinning weight. So for the space around them, they will influence them equally. So for a point that would have been, let's say here, let's say this point over here, after twisting, this red vertex would probably want to move it in this direction, and this blue would want to move it in this direction. Because they have similar weight, it will be somewhere in the middle, like is shown here. So to get back, so to get back, these weights come into play when trying to model the hand in canonical space to this hand in observable space to this hand in canonical space. And originally, my thought was that this canonical space is merely some different coordinate system, like a separate coordinate system where you simply separate out this hand and project it into that coordinate space as it is. But the authors tended to stress the point that the reason this this blend skinning comes into play, and the reason we have this deformation field is because, contrary to NeRF-based methods before, this is not about modeling a static scene. This is more about modeling a dynamic scene. So even though this is sort of vague in the paper, but for now, my sort of, from what I gather, it's that any kind of poses that you present in the observable space, this deformation field sort of tries to learn to sort of transform each of the joints in this observable space to this a generic hand pose in the canonical space. So let's say in observable space, you have these certain query points, and then after you have mapped them to, and then after you have moved that representation, sort of animated the motion using these blend weights and this transformation, sort of like this straight ray sort of will no longer be, the corresponding points will no longer be in a straight line anymore. They sort of get deformed. So I suppose deformation field sort of learns about appropriate hand representation via learning to map all kinds of different poses into one standard hand pose. So yeah, like I said before, when you given a particular pose, which would be the 3D coordinates of the 16 hand joints, and the sample, the x coordinate in the observable space, Mano will give you a mesh, which you use as an input in this deformation field. But so now let's get into the detailed operation. So let's say we have a mesh, for example, this one. Then we want to query a particular point, x 3D coordinate in this mesh, but this particular coordinate will not exactly be on any of these polygons or any of the surface on this mesh. So what you do is you get to the closest facet on this mesh. So a facet would be a particular space that is sort of even straight, that is enclosed by one polygon. So you get to the closest facet of your query point in observable space, and then you sort of try to get what the blend weights would be for that particular point for all the 16 joints through something called barycentric interpolation. And then when you have these weights calculated, then you can just use them here, and then you can loop over every 16 of those joints and use those blend weights and multiply with a transformation matrix. And then result of this will be your query point mapped to the canonical space. And this transformation matrix, I suppose, is a learnable parameter. But then another issue comes is that because you have sort of picked the nearest facet, not the exact x coordinate, because there might not be mesh in that x coordinate, and then you do this barycentric interpolation, this whole operation, even though it has been modeled as a linear transformation, will no longer actually be a linear transformation. So what it actually is a nonlinear transformation that you have represented as a linear. So it will have some errors. And to account for that amount of error, they use this another MLP, this FE, and then and then as you can see, this FE takes as an input first the canonical x coordinate and the pose, and then you add it to what you calculated, this x scan in the previous step, to get this new x scan. So but as you can see, there's a new transformation applied both to this x scan and this pose. So what this transformation is for is to, let's say, it's sort of to transform the left hand in a manner in the canonical space so that it overlays perfectly on top of the other hand. So that's all the purpose of this transformation. And yeah, you can see this. Yeah, this is the overall view of this deformation field. First, from an observable space, you put in an x coordinate and then the pose, and then you find the transform blend weights, and then you get the output and get it. You use the pose as well as the output here, and then you feed them into this error network, and then you finally get your canonical point after this operation. So yeah, I suppose we have covered like this part here that you get from Mano and the output of this deformation field. So, and then we have mapped this space already to this canonical NeRF. And then the next part is the depth part. So this comes into play here. So like I said earlier, since NeRF is a volumetric continuous representation, you can already compute a depth map from it. And this depth map is Z hat R. And since you already have generated a mesh from Mano, and then since mesh is also a 3D representation, you can also calculate depth from that mesh representation. So that mesh representation's depth is used as is modeled as the pseudo depth map, which is the ground truth, and you compare it with the depth map that you calculate out of this volumetric representation of NeRF. And the reason we do this is that so in their setting, they try to take maybe 6-7 images from around a particular scene, and then since there are very few images around it, what they claim is that NeRF tends to sort of fail to capture the geometry accurately from such few images. So they enforce the depth constraint too, so that the geometry would be more accurately captured. So yeah, I suppose I've already explained all of this. So again, so this is the point to look at the way we get the depth representation from our volume density that NeRF has generated. So if you notice, like this ZR is sort of similar to the original NeRF representation of the CR, where for query points and for some generated corresponding volume density, you use the color prediction and then you integrate over it, and then you get this color value. But in case of in here, the only difference is that you replace the color instead with T, which are denoted as the depth. And when you integrate over it, you get the estimated depth. So yeah, depth part has also been covered. Up next would be neural feature distillation. So neural feature distillation, so that would be this part over here, where the ground truth is generated from a pre-trained teacher. And this color feature, let's get into it. So typically the purpose of this neural feature distillation component is that typically NeRF just models X coordinates to color and volume density, but they claim that like just getting color is too naive of sorts. Like, so they tried to capture more information. So they instead, what they did is they made the NeRF output a color feature, FC, which is a d-dimensional vector. And then they derive this FC, similar to how you derive the color from the this vector representation of volume density. And the way, again, since the NeRF, so for NeRF first generates this FC along query points of a particular array, and then you apply volume rendering again on top of it to get this f hat R, which is yeah, you can say is like the expected value of this FC. And the way you get the ground truth value for this FC is you use a pre-trained 2D network that would take as an input the training image for that particular viewing angle. And then they use Dino as that pre-trained model that they call the teacher network. And from second layer of Dino, they get whatever representation they get, and then they use PCA to sort of map it to a more lower dimension so that, and then they derive this ground truth for this FR. So yeah, this is again the earlier slides where we use two different MLPs to model the volume density and color. So as you can see, we have already talked about how we get this one, the feature distillation, and we already talked about how we get the canonical space representation, and then we have talked about this, and this is just the viewing angle. So we finally have everything to get output out of our MLP. And now finally the losses. So the losses are basically everything that we have calculated so far, and every pseudo ground truth that we have generated, we just find the gap of them. So this is just this is just the expected color representation. We have already talked about this, and this is simply the gap loss for the depth map, and this is like simple like smoothing L1 loss, SLL. And we have also talked about the distillations, and again, you find an L2 loss among these two. And then, yeah, over here, we find loss for variance of the C, because what the authors say is model is prone to a local optimum where all the pixels on the target are converged to the same mean color. So they take a variance-based loss here. And then for this loss here, so essentially what this means is that the purpose of this loss is that they found that in sometimes around the representation of the hand, they find some fog-like semi-transparent structures, which are sort of like noise, you can say. So to avoid that, they applied this loss, where this loss essentially encourages the volumetric representation to either be 0 or 1, so that either there is a solid object, such as the hand, or there's nothing at all, so that we don't get those semi-transparent structures outside our hand's representation. And then that animation using those blending weights, like the operation that we did over there, we use that as the regularizer. Yeah, that's about it. And for experiments, the data set they used is interhand. It's called, it has 2.6 million images of this dimension. So they compared with a lot of other methods, but what they claim is that none of these methods were originally meant for modeling sort of dynamic movements of a hand. So they had to like just make some minor changes that like apply those settings into their setting, and these are the results they generated. These are for like, and this refers to how many images of those scene, including hands, that they used, and pretty much in every one of them, yeah, this HandNeRF beats them all. So yeah, that's it from me.
Have you achieved any generated image?
Generated image, they don't have much qualitative image to begin with. Most of the quality image they have are like, it's just representation of exactly this with maybe more different titles, but I suppose we can go and take a look. So yeah, this is the representation, especially for like cases where there are two hands involved. It tends to be like really bad for the other methods, but
They generated the right image from the left image. What is the original thing? What is the
oh, this is the ground truth, and this is the generated result for our HandNeRF.
yeah, but what is right column and what is left?
What is right column and what is left column? Oh,
Where is hands are generated from? What is the input?
oh, what is this input? The inputs are usually just so for this data set they use, it has some 18 views from different directions. They use
For specific is difficult now.
Mhm.
In this figure three, what is the input?
In this, I guess it's just some select few number of inputs, but the rendered images, it seems, are for only, I suppose, the validation set. Maybe I'll have to.
They do not represent any input in this figure.
They do not represent any input. I suppose no. Maybe I don't think so. No.
So they represent only two random images from some video.
Actually,
Yeah.
same image from different angles.
Yeah.
There's two ends or same end but from different angles. Ticket the message. Quality.
Is thinking that the first one, the last one, is the input, and the right one, is the output.
I suppose that should not be the case because they use at least 4 inputs for every single case.
They have to use a four different views.
Yeah, yeah. Like in the experiment, like they try for 3 different values, 4, 7, and 10. So it's never less than 4.
There are ideas given four, at least four different image.
Yes.
Generate some new and images
Yes.
is not key.
Yes.
Like saying that ours, theirs is the previous.
Yes, that's what they show. Yeah. I suppose.
When we